How does adiabatic quantum computing find optimal solutions? Imagine solving a puzzle where you start with a simple picture and gradually transform it into a complex masterpiece. That's similar to what adiabatic quantum computing does to find the best answer to a problem. It begins with a basic quantum state that's easy to prepare. Then, it slowly changes the system's energy landscape so that the final state encodes the solution you want. The key here is the quantum adiabatic theorem, which says if the change is slow enough, the system stays in its lowest energy state, called the ground state, throughout the process. This is important because the ground state at the end contains the optimal solution. The process involves defining two Hamiltonians, which are like energy maps of the system. The initial Hamiltonian is simple, with a known ground state that's easy to set up. The final Hamiltonian is designed to representing the problem you want to solve, with its ground state corresponding to the best solution. You start by preparing the system in the ground state of the initial Hamiltonian. Then, over a carefully controlled period, you gradually morph the initial Hamiltonian into the final one. Because the evolution is slow enough, the system remains in the ground state during this transformation. When you measure the system at the end, the result reveals the optimal solution encoded in that final ground state. The speed of this change is very important. If you go too fast, the system might jump into higher energy states, which can lead to incorrect answers. The minimum energy gap between the ground state and the first excited state during the process determines how slow the evolution must be. Smaller gaps mean you need to go even slower to stay in the ground state. This makes the process more time-consuming but more accurate. Unlike traditional quantum computers that use discrete steps with quantum gates, adiabatic quantum computing relies on continuous changes in the system's energy landscape. This approach can be more resistant to certain types of noise and errors, making it a promising method for solving complex problems. Devices like those made by D-Wave use this technique with networks of superconducting qubits. They are used to tackle real-world challenges such as optimizing routes, financial modeling, and machine learning tasks, where finding the best solution among many possibilities is essential. In short, adiabatic quantum computing finds the best solutions by turning a problem into an energy landscape, starting in a simple state, and slowly transforming it so the system ends in the lowest energy state. That final state holds the answer you're after, all while taking advantage of quantum mechanics to explore many options at once. This method offers a different way to solve problems efficiently while being more robust against some errors that can affect other types of quantum computers.